and the amide. Okay? So the driving force, as in many reactions we've seen, is to regenerate generate the carbon-oxygen double bond. So this goes by in a stepwise manner. So let me write a bond where. Actually, no, this is under acidic conditions where you first protonate on nitrogen. So this is actually the acid catalyzed. It's identical to the acid catalyzed amine hydrolysis, which goes by first protonating on nitrogen, then water attacking at carbon. Getting into conflict with my arrows here, but this is this first step. This now forms the aminomine. And now this is attacked by water. No. Sorry. Don't need water. You could do water, but it's more cumbersome than you can do it directly from the hydroxide function. And that gives you the amide. First, as the protonated amide, and then proton comes off, and that gives you the amide. And at the amide stage, we just can keep on going. Now, as it turns out, the initial sequence of turning the nitrile into the amide is faster than the subsequent hydrolysis of this to the final carboxylic acid. So if you want to, you can isolate the amide. So actually, nitriles are precursors to amides. And so if you want to actually make an amide rather than the carboxylic acid in the hydrology steps examples that we've shown, that's perfectly fine. You can follow this by NMR or any appropriate method, and you can stop at the amide stage and isolate the stuff perfectly well. So the next step, hydrolyzing this, requires refluxing water, typically, as we have discussed before. Polypeptides are hydrolyzed in boiling 3-normal HCl, whereas this hydrolysis occurs under milder conditions. 40, 50 degrees is fine, and so you can isolate that, and then we can continue if you want to. Now, notice that, as usual, in acid-catalyzed mechanisms, we first protonate to activate the electrophilic carbon such that it gets attacked by water, which is a relatively poor nucleophile. So we spiffy up the electrophile to be able to react with water. When we do the base-catalyzed mechanism, we have typically a negatively charged species, in this case always hydroxide, or an aqueous solution always hydroxide. That's a super good nucleophile already. We don't need to activate the nitrile. Okay? So it attacks the nitrile directly. Otherwise, the mechanism is very similar. So here, first we protonate, then we add water/hydroxide after deprotonation. In the base-catalyzed mechanism, we first add hydroxide, and then we protonate. Okay? So this intermediate is then protonated, and we are at this stage here, which is nothing else but exactly the same as that, which is the tautomer of the amide. And so in the base-catalyzed tautomerization of this going to that, we start with deprotonating first, and then you get 2 resonance forms of the corresponding allylic anion, and you protonate on nitrogen to get this guy. Up here, remember, we protonate first, and then we deprotonate. Down here, we deprotonate first, then we protonate. It's always the same. Okay? And then again, this guy, we've learned how to do the base-catalyzed hydrolysis of an amide. It's hydroxide attacking, addition, elimination. Okay, so that's all we're actually going to talk about for nitriles. It's just hydrolysis, because part of their usefulness is to actually make either carboxylic acid amides or carboxylic acids. One can add organometallic reagents, as we have done in a number of cases now. Remember, for acyl halides, we added cuprates to make ketones. For esters, we added Grignards twice to make symmetrical tertiary or secondary alcohols. Or we added, we just did Grignards, right? And in this case, we can also add reagents, and the most popular reaction actually is to add our classic organometallics, alkyl lithium and Grignard reagents. And what they do is they add to the CN triple bond exactly the way you would have predicted it, namely the nucleophile R adds to the carbon and the metal winds up on the heteroatom. And you get this. And it turns out that this now, because it's negatively charged, does not react with more alkyl lithium or Grignard reagent. It's stable, it just sits there because it's negative. So the Grignard doesn't want to attack a negative charge, Coulomb's law, repulsion. Okay? So this is actually stable in the pot, and then you dump in water, and it gives you first the amine by immediate protonation, and the amine, of course, is not stable in the presence of either acidic or basic water, and it hydrolyzes to the ketone. So what we have is yet another ketone synthesis, where you basically, in a general scheme, here's the ketone, you can control what's on either side of the ketone, not unlike what we learned with acyl halides and cuprates, where we also control left side and right side. Here we're controlling left side via the nitrile, and the right side via the Grignard, via the organometallic. And then remember, the nitrile, of course, is derived potentially by SN2 from the haloalkane, and so this gives you an additional, very general way of constructing ketones. And remember, we already mentioned that in the method where we used acyl halides and cuprates. Retrosynthetically, these are great steps, because you can basically cleave on either side of a ketone and cut a molecule. If the ketone is pretty much, the carbonyl is pretty much in the middle of the molecule, you cut it into 2 halves, 2 semi-equally sized portions. And that is part of that's a great advantage retrosynthetically, because you get smaller pieces more readily. So here's an example. You take acetonitrile or ethane nitrile with this pentyl Grignard, out comes 2-heptanone. And of course, if we can do organometallic additions, surely one has to be able to do hydride additions. And here again, it's an issue of control with a modified hydride. And lucky for you, there are 2 reagents that do this that we've already encountered. This lithium aluminum tertiary butoxy hydride, where this is typically a tertiary butoxy group, that we used in the selective single addition of hydride to acyl halides to make aldehydes. Or dibol, diisobutyl aluminum hydrides, the common name. This is, of course, the 2-methyl propyl group. that we used in the selective reduction of esters to give the same single hydride addition. Then we work up the stuff, and you're at the oxidation state of an aldehyde. So in both cases, acetyl halides and esters, we got aldehydes. While you can also do this for nitriles, and both reagents work quite well. By the way, I should mention that it's perfectly fine for you to use the term diol, since we are accepting you using the terms NBS and LDA and PCC. Anything else? LH, yeah, okay. So you can use those, okay? And in part because I don't want you to, it's very easy to do what I call typos in exams if you write the structure wrong for some reason, okay? The wrong branching or something. And we don't want to penalize for that, so I'm granting you the abbreviations, okay? So as long as you vaguely know what these guys look like, okay? And certainly know what they do. So here's an example. This cyclopropane nitrile, which is reasonably sensitive with diol, gives you the corresponding aldehyde in good yields. So this is now with modified, more selective, less reactive hydrides. What happens if we do the usual atomic bomb on it? Well, when you do that, it goes all the way to the amine. So it just grinds right through. It does a single addition, and it doesn't care that there's an imine aluminum, imine anion up there. The hydride is so strong on hydride reagents that it just reacts, it attacks again. Okay, so you get double addition of hydride, and the whole thing, the triple bond, is completely reduced to the corresponding amine function. Since it's a triple bond, it's actually also reactive in catalytic hydrogenations, just like alkynes. So you can do an ordinary catalytic hydrogenation also. You don't need the hydride. Platinum oxide, the so-called Adams catalyst, was one of the reagents that you learned about in catalytic hydrogenation of alkenes, but also alkynes. And other catalysts will work. Okay? So you can just do catalytic hydrogenation, same thing happens. You hydrogenate off the two pi bonds, and you get the corresponding saturated amine. So retrosynthetically, whenever you see a unit like this, think, this could be a nitrile. Remember that we could arbitrarily throw in a retrosynthetic step triple bonds and double bonds and carbonyls because we know how to remove them in the last step. So this is also true for CN triple bonds. So if you have an amine hanging off, of course it has to be a primary amine, you can turn it into a triple bond as a nitrile, and that gives you some added flexibility because nitriles, you introduce them by SM2. So you can keep on going. So you think of this, think of that, therefore this is the precursor, and again, you can go back to a hydrocarbon. So here's some specific examples. I pulled these out of the literature for the same substrate to see whether there's any particular difference in efficiency or yield, and they're about the same. LAH gave one paper 85%, platinum hydrogenation 96%. And I think at the scale that this was run, these are volatile compounds. If you have to do distillation, I think these guys were just a little sloppy and lost a little bit. But in the end, it's the same. So that's as far as I wanted to go for the exam. Okay, so it's the end of 20. And while we will start today with 21, it won't be in the exam. Now, some of the practice midterms, so it's the same scenario that we encountered in exam 1, will have 21 in them. This includes, I think, includes the last midterm that I gave 2 years ago, 2012. There we had the second midterm later, and so 21 was part of the agenda. So there will be some questions pertaining to 21, so ignore those. Okay? And that's true for some of the other midterms. It varied from semester to semester, so you have to cope with that. And so let me look at that exam to give you a feel of what's to come. I guess that's good enough. The exam will be in layout identical, okay, to this exam here from 2012. The only difference is the first page will not have this stuff, the numbers here, because we're using GradeScope for grading. But otherwise, we're starting with a 30-pointer as usual. The nomenclature, this initial line, as I recall, is totally unchanged. So, think about cis and trans, EOZ, ROS, and you're supposed to do IUPAC naming. Okay? So there will be some fairly simple examples of substituents. So this is a butanoic acid, and you plug in the substituents, and occasionally there will be RNS kind of questions. And so here you have to think about an N-alkyl group for an amide. Here was a cyclopentanone with a stereocenter. This one, oxo, so this one is an ester. So remember, esters are called alkyl alkanoids, and so there will be an ester with substituents. And so remember, oxo is part of a substituent naming for an oxygen that's bound by a double bond. Okay? And since esters have priority over carbonyls, the carbonyl is named as an oxo appendage. Here's a nitrile, and you can see that nitrile has another function, but it's a lower priority function. It's not another carboxy function, so it's an alkyne. So it's an ein nitrile. So question 2 is similar to, I think it was question 5 or 6 in exam 1, but it's the same setup. It's retrosynthetic disconnection. So we have in the layout, in the exam you'll see will be the same as in this exam. So I switch things around. In exam 1, I had the wiggly line guys on the left, and the answer was going to be on the right. Here, I'm putting it on the left to be more in conformation with the fact that this goes back. And this arrow should point from right to left, since it's a retrosynthetic analysis. And that's, you have the chlorobutane example that you saw in exam 1 as the model that you follow. But I hope you all have gotten this. One caveat that some of you fell into in this box, that you shouldn't write a synthetic sequence. 1, 2, 3, 4, 5 with all kinds of reagents. That's like a synthesis problem. They're just reagent A plus reagent B reacting should give what you get. Okay? So don't go further back. All right, so we'll have stuff like this, Michael additions, aldols. Here's an example from chapter 21, so ignore this one. So 3 will be vocabulary, so there are 10 of them. And so it's a straightforward, either starting material or the reagents or the products are missing, and you fill them in to the boxes. Some of them have 1, 2, 3 or 1, 2. And otherwise pretty straightforward. So learn your vocabulary because you can really get a lot of points in this question. And then by far the strongest emphasis, and this is a switch also from exam 1, will be on synthesis and mechanisms. So we now have 3 each worth 60 points, total of 120 points for these 2 sections. Okay, so about half the exam will be synthesis and mechanisms. So we start with mechanisms and then detail step by step And I should say, so don't totally freak out, some of those will be straight out of lecture, such as this one. Okay? We just did this example. Okay? So I want you to reproduce what we just did here. Okay? Acetonitrile with base hydrolysis. So there'll be at least 3 of those for in both mechanisms and syntheses that are essentially straight out lecture. And even in the vocabulary ones, there'll be examples that are straight out lecture. So if you kept up with your lecture notes, you're okay. Here's another one straight out lecture, aldol addition. Okay? Just the aldol addition mechanism for that. So then we have synthesis, and there'll be multiple steps, and there are several solutions to the problem. If you don't know how to tackle it one way that you think you should be tackling it, try something else. Okay? So because you might get there in just a roundabout way. We already, Fred and I and Marianne looked at the exam that I wrote, and there was one problem for synthesis where I had a solution, but they came up independently with 2 different others. Okay? So this is all part of the key, and we discussed it during the grading session. If what you write is reasonable and it gets you there, you get full credit. Okay? In fact, I'm delighted if you come up with stuff that we haven't thought about. All right, so there are 3 of those, and then the end is just a multiple choice. And it's always the same, that multiple choice. It picks on nucleophilic addition increases in the order, and then there are all these carboxylic acid derivatives, or acidity increases in the order. So try to remember the sequence 5, 10, 15, 20, 25 roughly, so you know where they fall. I'm not going to ask you numbers, but it helps you set up a hierarchy. Bulkiness increases in the order from various stuff like that. Okay? Pretty straightforward. And since it's multiple choice, you can do this again like you passed your driving DMV exam by exclusion, because 3 answers will be blatantly stupid, so it can only be the 4th. So focus on the least, what appears to be the least stupid answer. And then there's a cartoon, and that's it. Let's have a break.
Over your practice exam, and one of the questions that you actually just showed on the board was
I'll ask now. Has anybody had problems with the webcast? Especially is it the last one? Just the last one. The others work, right? Yes? So when you click, it doesn't work? Okay, I'll call it in. Okay, so here now, we're actually coming to the end of an intense road. The second third of this course is the most intense part. After that, actually, we start to coast. So rejoice, things are getting easier. This is also the last function that we'll discuss as a unified functional group, namely the amines. And some of it, or a fair amount of it, will be repetition. So I'm just summarizing everything that pertains to amines that we already saw in the prior, 800 pages, and add a couple of additional reactions that are there. Amines are extremely important in biological applications and medicinal applications. I mentioned it to you before that about it's estimated 85% or so of all medications, all drugs contain nitrogen. And part of that is the unique balance of